All right, let's check out the audio. The audio is good. All right, let me adjust this camera for y'all and we will get going. What's it doing here? Why do we have an infinite hallway? Oh, I see. All right, let me just adjust the camera. Good. And there we go. Okay. All right, sweet. My name is Justin Hill. I'll be your Cal 1 professor for the next 5 weeks. 5 weeks is a very short time to do any math class, not just kind of Cal 1, but really anything that you're going to go for. So I'm saying that not to say, saying that to say, welcome to Cal 1 Summer 2025 with Justin Hill. So welcome to it. Just know we are going to be going fast. It's gonna be a lot of stuff at once. But you guys have already gone through the orientation module, so you have an idea of everything we're going to be doing in this class outside of the lectures. We're going to have a midterm exam. We're going to have a final. Um, but once you're done with the orientation module, again, yeah, so you guys have done the discussion, you've done the syllabus quiz. So the rest of this semester, each week is going to be roughly the same. So each week is going to be, I'm going to give you guys a lecture or two or three or four, depending on how, what we're doing and how many it takes me to get there. But I'm going to give you guys a bevy of lectures. You guys are going to see it in your Canvas module. So you guys can see the week 1 module now. And for every week, it's going to look roughly the same. You're going to have a page that gives you the lectures that you need. And then you're going to have the little buttons for you, the little pages with your homework. So with the buttons for you to press so you can get into Cengage and start working through your homework. So this week 1 is watch the lectures, do the homework, and your gravy, right? And then week 2 is going to be the same thing. Get into the homework to the lectures page, watch the lectures, do the homework, and your gravy, right? So then we'll get to week 3, which we'll start out with our midterm that week. You'll be taking the midterm that Thursday. When we get closer to that week, I'll message you guys about how we're going to be doing the test. As you guys kind of saw in the syllabus, though, and as I mentioned in your welcome email, I do my tests over Zoom. So you're not doing a test online using Respondus. You're going to be doing it live with me over Zoom. So that third week, on Thursday of that week, you guys are going to be taking your midterms. So what I'll do is about a week before that, hopefully, I'll send you guys out a message with the time slots for that day that you guys can zoom in. And you'll zoom in, we'll take the test, but then you'll still have some lectures. Once the test is done, that's Thursday of week 3. You're still going to have some lectures and still some homework to get done by the end of the weekend. And then week 4, back to the same deal. Click on the lectures page, run through the lectures, do the homework. And then week 5, obviously, is the week of our final. I'm going to try to make it so you guys don't have any lectures and homework to work through that last week. But no promise there. For this class, it's actually, so I'm teaching 3 classes, by the way. I'm teaching 3 classes for this summer 2 session, 3 online classes, like yours, Cal 1, Cal 2, and differential equations. For y'all's class, Cal 1, the way that this material is laid out, I think it will be possible for me to for us to get as much done week 4 as we need to, so that we don't have to do any lectures week 5. But no promise there. But even if we do, so if we do have a couple sections, a couple lectures to get through on week 5, I'm actually just going to give you guys basically 2 days to do that. So same deal, get into the lectures, work the homework in Cengage, and then you'll have you'll have a review up. So by the way, on week 3, you also have a review up for that midterm. So on final week, you'll have a review up for the final. And then again, on Thursday of week 5, we'll be taking the final, and same deal, we'll be zooming in for that. So again, that's sort of the rough layout of the class. Like I said, it's fast, it's a lot of material. So let's get it. So what I want to look at today is actually, this first week you have 4 sections, 2, 2, 2, 3, 2, 4, 2, 5, but they're all about limits. So what I want to do with this first week is basically I should be able to do everything you need for these sections in 2 lectures. First thing I want to do is I want to talk about limits, this idea of limits. And we'll kind of get into that. And then what we want to look at is how do we find limits algebraically. So you're going to see a lot of this class, by the way. So, I'm saying welcome to the summer. I'm also saying welcome to calculus. And what you're going to see with calculus in general, so calculus only overall, not even just this class, only introduces really 2 new ideas to you mathematically. It introduces the idea of the derivative and introduces the idea of the integral. What you're going to see with the problems that you do in calculus is that they are 25% new idea, new material, 75% old hat, 75% algebra and pre-calculus. So all those things that you guys learned in algebra and pre-calculus, all those skills, all those ideas, all those concepts, but especially all those kind of skills and way to work through problems, every single one of the problems you're going to look at in calculus is going to involve those. If you got through those classes, you felt like, I got through the classes, I did the thing, I sort of understand what's going on, but I don't feel like I mastered what's going on. Then we're gonna do sort of a quick, we can't even do a quick recourse in mastering that stuff, but as you do these problems, you're gonna become a master at all of those algebra and pre-cal skills because you have to. The way calculus is designed is, it is in order, you're going to get these new ideas, but in order to do those new ideas, you need to do a crap load of algebra and pre-calculus technique. So this class, just by nature, the way it's built, it's assuming that you've mastered those techniques. And if you haven't, that's okay. As we do the problems, I'll kind of talk through some of that stuff, and you guys will become a master of those techniques because you have to. But not only just because you have to, because you're just going to get a ton of practice with those techniques. So good. So let's start out. Looking at limits, and give me a second to set everything up. Now I'm curious, is it going to do that every time? Yeah, well, okay. Interesting. Where do I want to be? Let's start here. Let's get this. All right, so let's start talking about the idea of limits. So what I have here, so I want to focus on this picture you kind of see on 23. In fact, give me a second. Is this? Give me a second. Let me accept all the cookies and do all the things we need to do here. I should be able to size this. Gives me PC. Be a second. It's just not working. Okay. Let's see how big that is. The other thing, let me check how the video looks on this. If it's grainy or if it's good. Just in case y'all, well, looks good from my side. But let's do this just in case. Yeah, it should be good. All right. Give me a second to figure out. I even used this room before with this technology. It allowed me to modify the touch screen. Now it's not doing it. It's full screen. All right, well, I can't zoom in on this, which is kind of a shot I'd be able to do on this. So just as you're watching this video, make you zoom in on it. But I want to focus on this first image you see here, number 20. So we're going to talk about limits starting just looking at this kind of graph. So this is a function. So notice they've kind of highlighted what the function is for you. This is the function 4 minus x. You guys are well familiar with functions. Again, you've done algebra, you've done pre-cal. It literally has been a study of functions, right? You've looked at these functions, how to graph them, how to solve them, things you can do with them, etc. So you'll see too, though, as we go through calculus, we're going to look at all these functions again. So your linear functions, quadratic functions, polynomials, rationals, trigonometric functions, sine, cosine, cotangent, all that good stuff. We are going to look at all those functions again, and we're basically just going to figure out how to do some new things with them. So we're going to talk about limits in this chapter, but then, like I said, again, the main thing in this class in particular is we're going to figure out how to find derivatives of those functions. But that means that we're going to look at those functions again. You've seen them, you know what they are. Now let's do something new. So this is a nice, good old linear function, 4 minus x. And so they're asking for, so I want you first just to notice this sort of the notation here. So they're asking for the limit as x approaches 3 of 4 minus x. And even though this is a video, I know there's nobody on the other, this is not a remote class, there's nobody who can respond to me. I still want to ask questions as we go. I still want to ask you guys questions. So when I ask questions, if you want, take a second, pause the video, kind of answer the question in your head or answer the question out loud, shout at the screen if you need to, but answer the question. And then hear my thoughts and kind of hear what I have to say off that and compare and contrast. But actually it doesn't matter if you get the question correct. What matters is whatever you say, whatever you think on the question, then kind of take my thoughts and, or, look at what's true about the thing and what's happening. And just be like, okay, I was right. That's awesome. It made sense because of such and such, or I didn't get that idea right there. So why didn't I get it right? Well, where were my thoughts? And how do I change my thoughts to kind of the vein, the direction, the idea that's being brought up. I've noticed in general, again, this is just a saved video that's going to be, you guys are going to be using in Elite broadcasts in other places. But what I've noticed with a lot of students in my 15 years of teaching now is you guys are so dogmatic, you're so worried about getting the right answer. You don't realize that you learn a shitload in this life from the wrong answers. The right answer is awesome. It tells you, hey, my thinking was correct there. My thinking is going in the right direction. I keep going in that direction. It should keep working. It tells you that you understood something, but it doesn't get you new ideas. It doesn't get you new learning. It doesn't show you a different branch, a different direction. It doesn't really create anything new, right? So that's when you're wrong about something, what it does is it's an opportunity for you to create something new, for you to figure out, well, if my thinking didn't work there, what's the right thing? If the direction I was thinking didn't work, why didn't it work? I always tell my students, one of the hugest things that you learn from is why was I wrong? Why didn't it work? You learn more from that than you learn from understanding why you were right. So if you're wrong, why was I wrong? Why was my thinking and idea not appropriate or just didn't work for this situation, right? And then again, compare contrast. So what's the right idea? What's the right thought? Why does that work for this situation? That kind of compare and contrast, those two questions and answering those questions for yourself. Why did my thinking not work? Why did that solution not work or that method not work? And why is the correct method doesn't work? Why does that thinking work? That'll teach you more, not just in calculus, but in this life than anything else, honestly. So please value being wrong. Don't worry about being wrong. So again, going back to what I was saying about this, see so many students so freaked out over being wrong. And just really, I mean, like, you really don't need to be freaked out. You have such an opportunity to learn from being wrong. So again, when I ask these questions, I'm getting back to my original thought, when I ask these questions, answer. And then go from there. If you're wrong, figure out why you were wrong, and you're gonna learn a shitload. And if you're right, figure out why you were right. And keep reusing that thought, that pattern, that idea, etc. So, okay, so let me remember what question I was gonna ask you guys. So we're talking about a linear function called minus x. We want the limit as x approaches 3. So I guess my question maybe, and I guess first question is, well, what do you think that means? So like, this is verbiage, this is symbology that you don't know yet. But you're smart, so you figured out a lot of stuff in life, you can make a good guess. What do you think they mean by, what's the limit as x approaches 3? And thinking of the word limit sort of means like, some sort of, right, some sort of end, or some sort of maybe end to a journey or end to a process, or boundary, a wall, something like that, a fence. So what in calculus, when we're talking about a limit, or in mathematics, I'll say in calculus, calculus is just a portion of mathematics, right? So in mathematics, when we talk about a limit, in some sense, we mean something like that. So the idea of when they say, what is the limit as x approaches 3? So again, I want you to just kind of, I'm teaching you how to read this. But again, tell my students math is a language. And so usually the beginning of a math class, that's a lot of what you're doing is actually just learning how to read what they're saying, right? So, so the way you read this is, what is the limit as x approaches 3 of 4 minus x? And so like I said, limit sort of means kind of an end, a boundary, a barrier, the end to a journey. So the idea is on this function, which right now we have represented as a picture, as a graph, on this function, as you get closer and closer to 3, so what they mean by there is they're saying as x approaches 3, so as you get closer and closer to the x value being 3, what is the y value? What's the y value that you see with that x value of 3? And as you can see here, as we get closer and closer to an x value of 3, we get closer and closer to this point, right? But even, we'll talk about, even if that point isn't there, as we get closer and closer to an x value of 3 from the left, so notice that there's 2 different directions we can do here. So if we're thinking about getting close to an x value of 3, we can come from the left, or we can come from the right. We're going to see that that actually matters. So there are 2 different ways to approach this, and you need to keep both in mind. Now on this function, 4 minus x, as I approach from the left, I get closer and closer to x being 3. What's the y value? What's the end? What's the y value that you see there? Good. And hopefully you kind of look at this and say, well, obviously at 3, the y value is 1, and it seems then that, so not only is the y value 1, but then if I'm rolling my finger along this slope, then my y values are starting high and getting closer and closer to 1 on the left, and then on the right they're starting low, but still getting closer and closer to 1. So we kind of have 2 behaviors happening. From the left, the y values start higher and get closer and closer to 1, and on the right, they start lower and get closer and closer to 1. But either way, my y value is getting closer and closer to the same thing. It's getting closer and closer to 1. And so the limits as x approaches 3 for 4 minus x is going to be 1. What is the y value that you see there that's getting closer and closer? I want you to notice that, let's put it out, that in order to have, let me use full words on this. In order to have this limit, so they just asked for a limit, you looked at the graph and you figured out that limit is 1. In order for that limit to be there, to exist, for me to be able to tell you, or you to be able to tell me, hey, this limit is 1, there were a couple things that we naturally did in Online. first thing was the limit from the left. Had to exist. So there had to be a limit from the left. And the limit from the right had to exist. I know visually it's probably redundant to you, but just kind of go with me on this. I mean, that's what we did though is when I was looking for that limit, I kind of looked from the left, what's happening, from the right, what's happening, and then I just said, what's the number? So from the limits from the right had to exist. And when I was looking, so again, I was talking about what is, what's the behavior from the left, and what's the value from the left, and what's the value from the right. I naturally talked about a value from the left or value from the right, and the key that we sort of in our mind logically worked through, but I didn't say, and maybe you didn't say. Key was that they both agreed on each other, right? So the limit from the left was a 1, the limit from the right was a 1. Therefore, my limit is 1. So it's like the limit from the left had to exist, the limit from the right had to exist, but they also have to agree on with each other. So the left limit has to equal the right limits. And I'll just shorten that by just saying left equals right. So if you have these three things, then you have a limit. The limit has to exist from the left, has to exist from the right, and they have to agree with each other. Now, this first picture, this first example that I'm giving you, it's kind of a duh example. It's pretty obvious, right? So it almost seems like, why would I even like talk about all this or write all this out? The limit from the left has to exist, the limit from the right has to exist, and the left has to go right. The reason I have to write that out is, so this is, like I said, this is kind of a duh example. And if you think back to your college algebra and pre-calc classes, a lot of functions sort of, there are a lot of functions sort of look roughly like this: linear, quadratic, or polynomial. But my point is, not every function is nice like this, and therefore not every function actually fits all of this. So for a limit to exist, you have to have a left limit, a right limit, and they have to agree to each other. And surprisingly, this is a duh example, but surprisingly, that's not, we have plenty of examples where that's not always true. It's not always the situation you want. So for instance, man, I really wish touch screen worked on this. So for example, let's go to example 25. So notice example 25 is actually a lot like example 23, or problem 23, or whatever that we were looking at. It is a linear function. Notice here actually, if you look at the piecewise function that I have defined here, notice the first part of it, 4 minus x, for everything except for x equals 2, that is exactly the function we were looking at in 20. The difference here is I've redefined f of 2. So when x equals 2, I've redefined f of x as 0 instead of whatever I would have got when I plugged in 4 minus 2. So we get this point. So we get a hole in the graph here. Get this extra point outside there. Now this problem is asking, what is the limit as x approaches 2 of f of x? So again, you want to think of, from the left, what's happening to the y value. So what would you guys say? So maybe you're seeing that from the left, again, we're starting high. My y value is starting high, and they're getting lower. They're kind of going lower and lower. They're getting closer and closer to, it looks like, a y value 2. Now, again, because of that open circle, what we're saying actually is that this line actually never gets quite there. Your y values never get quite to 2. but they get closer and closer to two. They would literally what this again what this open circle means that from previous class is it means we're getting as close as we can to the values of that point or to that point without ever actually reaching it. So it's not just that the y values are getting closer and closer to two, they're gonna get as close as you can get to two without actually becoming two. Good. So let's kind of test again this definition. So this what I've given you guys is a definition for a limit. If you look in the book, there's a more formal definition. This says everything in the formal definition, just says it in a little more colloquial way. So this is our definition of a limit. This tells us not only what a limit is, but really when it exists. So the first thing to check is, does the limit exist from the left? And what you guys just told me is, yes, it does exist from the left. Maybe I don't have that point there. So the first thing to recognize when we're talking about limits is, again, on that first example, you had a line and they just marked the point that you were kind of looking for, right? The point doesn't have to be there. So the point we're looking for is basically 2, 2. It is not there on the graph. We actually get 2, 0. That doesn't mean the limit doesn't exist. So that's the first thing I want to clarify. Is again with that first example, because it was so duh, you just think, okay, see a line and I say the point, right? But then the question is, the first clarification is, what if the point doesn't exist? That the first thought then is maybe that means the limit doesn't exist. Surprisingly, that's not true. The point doesn't need to be there for the limit to exist. The limit is, some of the verbiage when I've been asking you guys about the limit, some of the verbiage I've been using is I've been saying, what's happening to the y value? What's the behavior of the y value from the left? What's happening to the y value from the left? What's happening to the y value from the right? So a limit is not a point. A limit is not a number. A limit is a behavior. It's saying, as I move my x value closer and closer to the x value I want, what is the behavior of the y value? So the interesting thing is, the y values can get closer and closer to a number. If they get closer and closer to a number, the limit is that number. The point doesn't actually have to be there. That's the first thing to kind of digest for a second. So like I said, it's when I'm showing you guys this stuff, when I'm doing these lectures, I'm not just trying to get you guys to do a homework problem, right? Because you would actually suck at math if you just do a homework problem, right? Because you don't understand why you're doing it right. You don't understand the concepts and the ideas behind it. So again, what you'll see a lot of what I do in my lectures is, yeah, we're gonna do problems and we're gonna do ideas and concepts that get you the homework. But the ideas and concepts are actually really the key. And so I'm gonna major a lot on getting you to really connect with the ideas and concepts and why these things work and why they're true. So the first, hopefully, Oprah moment clarification sort of idea that you want to connect to here is that when I'm looking for a limit, it doesn't mean the point has to be there. A limit is not a point. A limit is a behavior. It's a trend. It's where is the number going? So from the left, the y value is going to 2. So the limit exists from the left. Does the limit exist from the right? From the right, my y values as my x value gets closer and closer to 2, as I go along this line, what is the y value getting closer and closer to? It's also getting closer and closer to 2. Good. So the limit from the right exists. Do they match? The two y values you just told me from the left and from the right, do they match each other? Yes, they do. Therefore, the limit exists. So I can say the limit is x approaches 2 for f of x here. The y value that we're getting closer and closer to from both sides is 2. Again, hopefully that rocks your world for a second. The point doesn't actually need to be there for the limit to exist. This idea, especially when we start talking about derivatives, you'll see is kind of, at least for me, when I was learning calculus, it's a revolutionary concept, honestly. It should rock your world. It should mess with your mind. That we can sort of have a trend in behavior, a sequence of numbers, numbers getting closer and closer to something, and that something then exists even though the point is not there. That something has meaning and value that we can use even though it's not there. So we're gonna, and then again, in this chapter, we're gonna do all this stuff about limits. I think a fair question by the end of the chapter is, what the hell is this good for? Like, what are we using this for, right? So I can answer a question, but what is this good for? You'll see in chapter 3 when we get to derivatives. So this idea of a limit is key kind of cornerstone concept we need to be able to do derivatives and then integrals when we get to calculus too. You need to be able to identify and have meaning for what is the behavior of a sequence of numbers as we get closer and closer to something. You need to be able to say that it's there, that it exists, that it's the answer, that it has real value, right? Even though the point doesn't necessarily exist or we can't visualize that. So this, again, I'm making a big deal about this point, but I'm making this big deal about this point because I'm sort of hopefully foreshadowing for you guys that this concept should be crazy in your head for a second, but it's a really absolutely necessary and important concept. There's a reason it's chapter 2 of this book. Everything you do with derivatives and integrals to start with, at least before you figure out the patterns, involves the limits. So we need to be able to identify when a limit exists. We also need to be able to identify when a limit doesn't exist and why it doesn't exist. But right now we're doing some examples where it does. And it's kind of a bunch of foreshadowing. But the limit from the left exists and it's 2, the limit from the right exists and it's 2, they match, and so I can say the limit equals 2. I don't actually need that right there. In fact, we could have defined this function simply, even without the other part of the piecewise function. Just 4 minus x for all x not equal to 2. And the limit would still be 2. Let's look at some examples. So 2 examples we've seen so far where the limit does exist. Let's look at some examples where it doesn't exist and kind of start to get an idea of why not. Look at 27. So this is the limit, they want the limit as x approaches to this function. So this function is kind of an interesting function. So they give you the picture here, which is nice of them. This is the absolute value of x minus 2 divided by x. So this is something you probably saw in a called algebra class once, twice maybe. Sort of an odd little function. You're going to see as we go through calculus. I was saying that calculus revisits all the functions you've seen, and we're going to start to answer some other questions about those functions, limits, derivatives, integrals. But what calculus also then does is says the world is not so simple, and the models, the functions, the equations that we use to model things are not always just a beautiful polynomial or a sine function or a cosine function or something like that. Sometimes it's an awkward combination of those functions. You might see something like this, an absolute value function divided by a polynomial, and when you divide them, that makes them a rational function, but it's a weird rational function because I have an absolute value there. So I mean, this is just some odd combination of functions, right? And you can even see on 28, we may not even look at 28, but if you look on 28, 28 is a rational function with an exponential function kind of thrown in there, right? So you're going to see that, you're going to start to see that a bit more. You can see that a lot in calculus. We take all these simple functions we've looked at and we say, let's just combine them in weird ways and see what happens. Let's see what we get out of it, right? But we do that because, again, if you guys have taken some physics and chemistry classes already, you know that a lot of the functions we end up using to model a lot of chemical processes and physical processes in the universe are odd combinations of simple functions that we know. Kind of mirrors in some ways the history of both science, but also just civilization and progress, right? So the Greeks defined simple machines, right? I think it was the Greeks who did that. But we have these simple machines, a screw, a lever, a pulley, etc. And then the next iteration is, what if I combine them together? What can I do with that, right? And then now we're taking combinations of machines and combinations of other machines, other simple machines, and we're putting them together with electronic circuits, right? So it's like we just keep making more complicated and complicated combinations of these simple elements, right? So when math is our way of sort of modeling reality, right? So in some ways we do the same thing. You have these simple elements, power functions, polynomials, rational functions, sines, cosines, and we combine them together and we kind of need to combine them together to model reality, because reality is not simple, it's complex. But we combine them together to model reality. And then we combine those combinations to get even better, maybe more accurate models of reality. So I'm just saying it sort of makes sense that not only is calculus going to do this just to have fun with you, right? But we have to do this. We have to do this if we want to model reality. Anyways, so let's look at 27. 27. This is also one way, by the way, to, well, actually, it's not a step function. I mean, this technically is what's called a step function, but it's not the way they usually define it. This is, I don't call it impulse function either. I gotta remember that. This step function, though, gets used a lot in electrical engineering, because it basically models sort of a switch being on and a switch being off, right? So anyways, so we want the limit as x approaches to this. And again, right now we're going to trust that, this is our graph of it. Graph is a nice way of sort of defining the whole function. We see the whole function. We lose some details in the numbers, but we see the whole function without having to play all the algebra, right? So let's figure out the limit as x approaches. So from the left, as you get closer and closer to x value of 2, what y value are you getting closer and closer to? Good. Notice that the y value here is going to be -1. And we're going to see it. We're going to see it in some of our next examples. But let me just go ahead and write. We've been talking about this left limit and this right limit, right? The limit from the left and the limit from the right. Let me make sure. I would split this one out. Make sure I write this. So there's actually a way to write those limits themselves, right? So let me write this up here for you. So the limits is x approaches 2. So if we want to say x approaches 2 from the left, so you say 2 minus. So you think about what they're doing there is you're thinking about a number line. And on a number line, in general, your negative numbers are kind of coming, those to the left are coming from the left, and the positive numbers are coming from the right. So when I say the limit is x approaches 2 minus, I'm saying x approaches 2 from the left, if my negative numbers are on the left. So my limit is x approaches 2 of this function, or 2 from the left. That's equal to -1. And if this is the way you write the limit is x approaches 2 from the left, what do you think is the way that you write the limit is x approaches 2 from the right? Good. Limit as x approaches 2 from the right should be 2 with a little plus there. Again, this is just symbology. It's just a way, this is literally language. This is the way we're going to read that, or the way we're going to signify that, so that when you read it the same as when I read it, as when the other student reads it, etc. But again, it also makes sense. Your positive numbers are on the right side of our number line, left to right. At least that's the random choice, or not random choice, but forgetting the word right now, but that's sort of the standard choice that we have. Not negative numbers on the left, positive numbers on the right. So the limit is 2 as x approaches 2 from the right for this function. What is that going to? So if you approach 2 from the right, what is that going to? Good. That's actually going to be +1. So the limit from the left hand exists, the limit from the right hand exists. But do they match each other? Good, they don't, obviously. Because they don't match each other, then this limit does not exist. Does not exist. They have to match each other. I have to be saying the same thing, right, from both sides. So this is one reason you might see for a function for the limit not exist. Is actually so again kind of a curious thing. It's not that the numbers aren't there. The limit exists from the left and it exists from the right. Key is they have to match each other, or else we're talking about two different things. Another reason why this limit may not exist. Actually, give me a second. Yeah, we can talk about that too. So let's actually look at 29. But let's start with 29. All right, so looking at 29, they're asking what is the limit as x approaches 0 of this function cosine of 1 over x? And this is a fun, so again, if you want to have fun with your graphing calculator or whatever whatever little app online you're using as a graphing calculator, plug this thing in. Notice that it's sort of like if you forget the middle for a moment, there's sort of the shape of a cosine function, but then it just does this thing. So what happens, does this thing where it just keeps bouncing up and down. So in some sense, it is a cosine function, but you're squishing, it's like you're basically progressively squishing the period of it. So the period, we're used to with the cosine and sine function, the period remaining constant, right? So the period is too high and it just keeps doing that. Or if you do some sort of, what do you call it, horizontal stretch on it, then we can adjust that period, right? The period remains the same infinitely, both left and right. So this is an interesting play on the function because basically what happens is your period out here is going to be a lot longer than your period here, longer than your period here, longer than your period here. So as you get closer and closer to 0, the period just gets infinitely smaller. And so if you think of a cosine function of that wave, you're getting that wave, you're getting those peaks and valleys, but you're getting them closer and closer to each other at a shorter and shorter period. So you get this progressively infinite, just kind of bounce up and down, right? So let's think about as x approaches 0 from the left. What's my limit? What would you guys say there? Good. And hopefully you're kind of either demurring on it or you're kind of like, wait, I don't think there is a limit, right? So the problem here is because this keeps going up and down, and it keeps going up and down kind of infinitely fast, there's not a single number that's getting to. So again, a limit is, like I said, again, it's not a number, it's not a, what do you call it, a point, it's a trend in behavior. It's saying it's kind of keeping track of that y value and seeing where it's going. And the problem here is it's going all over the place. It is going somewhere between -1 and 1, but it's just keeps going up and down. It doesn't ever really settle. So in this case, in the first case, we get to see where the limit from the left actually just doesn't exist. I can't say it's settled at some number. Keeps going up and down. So the left-hand limit doesn't exist. And you can see from the right hand, it doesn't exist either. So coming from the right, it's also doing that same behavior. Y value is just going up and down, up and down, up and down. And you never can really set a little small region where you can say it's definitely getting here. Y value is definitely getting here. So neither the left hand or right hand exists. I probably don't need to write this, but let me just write this. Help us with a couple later problems. So as we approach 0 from the left, this limit doesn't exist. The same with the right. Limit as x approaches 0 from the right, sine 1 over x does not exist. So notice, if those two limits don't exist, I don't even have anything to compare to say left equals right, but even more importantly, if those two limits don't exist, I can't say that there's an overall limit. doesn't, again, just doesn't even make any sense. It doesn't fit the definition or fit, when I say definition, I'm just saying what we need for this thing to be what we say it is, right? So as soon as one of these limits doesn't exist, done and over with, there is no. So this is another reason why your limit may not exist. On a previous example, we saw that the left hand and the right hand limits exist, but they didn't match each other. So that's one reason why your limit may not exist. But another reason is if either one of the left or right hand limits don't exist, then it definitely doesn't exist either. So does not exist. Another one to look at. Let's look at 30 really quick. We have, notice this is the basic tangent graph. They want the limit as x approaches pi over 2. So one idea to get into here, I do want to get into this, but give me a second. We may wait a second. Yes, maybe we don't. All right, so limit is x approaches pi over 2. So again, let's look from the left. So looking from the left at pi over 2. What would you say the limit is as x approaches pi over 2? What is that number getting to? Now I am really curious on you guys' things. Good. So some of you may be saying, well, the number keeps getting larger and larger. So like, again, it's not ending somewhere, right? Like it's not settling anywhere. I can't say a number that it's reaching, right? So you may be saying doesn't exist. Some of you might be saying infinity because from a college algebra class, you're probably used to not only the idea, but used to saying, well, I know that it's good. Sort of behavior of this is going to infinity. So in truth, if you said one of those two things, both your answers are correct. So in terms of, again, if I'm trying to say, what is the limit as x approaches pi over 2 from the left in x, what I'm trying to say is what number is it getting near, is it approaching, is it settling at, right? And so if you said that there is no number because it just keeps going higher, you are correct. There is no number that is settling at. And if you said infinity, unfortunately, or I say fortunately, you also are correct. So going back to, again, a college algebra class or a pre-calc class. So infinity is kind of an interesting thing in mathematics. Infinity is not a number. We never reach infinity, right? So like there isn't a number. There isn't a thing I can say, this is it. I've got it. I've got there. I've reached it. But it ends up that infinity is not only a useful concept, but we basically sort of talk about it and use it like a number. It is a place that you get to, right? So if your numbers keep getting larger and larger, we say that get to infinity. Now again, when we say that, it's like we're saying a true thing in our mind, but we're using words that are bad for it, right? You never get to infinity. Infinity means you never stop going. But we have this concept, we use this word infinity and this concept infinity to basically communicate that idea that we keep going when we never end. So there's sort of infinity is sort of this phantasmal, like process of keep going and you never end. So because of that, fortunately and unfortunately in mathematics, we actually talk about infinity as a number, as a concept. It's a place we get to, right? We never really get there, but it's a place we get to because every time we keep going without stopping, then that concept, that idea is the same. And if that concept and idea is the same, then I can give it a symbol. I can give it a symbol, then it has a word. And if it's a word, it's something I can talk about and manipulate and we can communicate about and think about, right? So that's what we do, not just with mathematics, but with language, right? I mean, we give words, symbols to concepts, things that and we can talk about, dissect, and figure and think about. Anyways, so infinity is both not a number, but it is a concept. It is a place that we get to. It's something we can talk about. So in terms of limits, it's something we can talk about with limits. So on this, we surprisingly don't say that the limit doesn't exist. We say that the limit is infinite. Because we're trying to say, yeah, there isn't a place we get to, but there is a concept, there is an idea, there is a place we get to. It's infinity. And if that still then is freaky to you, especially if you're on the side that said it doesn't exist, I actually would encourage you to let it be freaky to you for a good second. Not just a good second. Let it be freaky to you for this chapter. Give them the answer you know that they want, but let it be freaky to you. And then, especially as we get through starting to do a derivative, some of the freakiness is going to go away of that concept of sort of the limit being infinity. Because again, what you're going to see is that surprisingly, that answer, that concept, that idea is useful. And if it's useful for something in reality, then it at least settles our fears and anxiety about it, right? Like maybe we don't understand it fully, but it works and it's part of our reality. So I can at least shake its hand, say hi to it, be like, I don't understand you all the way, but you know, you're here. And you're part of, you're part of these things, in this case mathematics, but you're part of these things that work. So limits as x approaches. Now let's look at the limit as x approaches pi over 2 now from the right. And what would the limit as x approaches pi over 2 from the right be? Okay, so coming from the right, you kind of have this tan graph going down. So now again, let it be weird. So if you want to say that it doesn't exist, you're correct. It is going somewhere specific. And that specific place it's going is now not positive infinity, but negative infinity. So I can say that's negative infinity. So in terms of limits, I'm at least saying I at least have an answer for 1 and 2. Again, if you want to say it doesn't exist, I will not disagree with you mathematically. And like I said, let it be weird. Let that be your answer. But know that if we can say it goes to infinity or negative infinity, in terms of this definition, it works at least. We have a limit from the left and we have a limit from the right. But do they agree with each other? Good. No, they don't. So overall, then this limit does not exist. Negative infinity and positive infinity don't agree with each other. Unless you're in some higher, some particular portions of higher mathematics. But the limit doesn't exist here. Basically, again, the major thing, or the key thing here is you're not seeing the same behavior from the left to the right. You can't make up and down the same, match each other, right? Good. All right. So good. This not only had us talk about limits, but it has us talk about left and right limits, which is so I'm getting these sections from these problems from 2.2, but talking about left and right limits actually helps you answer some problems from, I think it's 2.3 or 2.4. No, 2.4, sorry. So what I'm going to do is let me switch to some problems from, I'm going to go find some exercises from 2.4 that are asking for left and right limits. And I'll have you guys work on those. So now that what you're going to see in 2.4 is they're going to ask you not this, they're going to ask you something like this. If you get something like this, just think about if they're asking for what's the limit from the left, then you don't need this right part of this. And then you don't even need the left equals right. So if they're asking for a left-hand limit, before we get to these problems, just think about this overall definition for a limit I've given you. If I'm asking for the limit from the left, then I don't need the limit from the right, and I don't need the left and right to match because now I don't need the right. So you just need to identify what's the limit from the left. And if I ask for the limit from the right, just need to identify the limit from the right. I don't need the left, and therefore I don't need the left to match the right. So I'm gonna give you guys two problems to kind of work through from 2.4 that are just left-hand limits and right-hand limits. So let me find those for you. So by the way, what I'm clicking on here, so this is the in Cengage, you guys have been given the ebook, and you also so you have a page with a little load button and the orientation module that you can click on for that. Also, when you're in Cengage, there's a place from your student view where you can just click on it and open it. But that's where I'm buying this stuff. So again, I'm going to give you guys a lecture for all this stuff, but realize that you have a whole book here, and I know it's not passe anymore. Not passe anymore to read through textbooks, but I'd say not just not passe. I totally understand from y'all's perspective that it doesn't seem necessary to actually read a textbook, especially for something like math or science. Maybe for English or history, but math and science, it's like you don't even need to really read these textbooks anymore. I would challenge you guys though that there's actually a lot to learn from the narrative in the textbook. So it's not just the examples and exercises, but there's a lot to learn from the narrative in the textbook. So I would actually challenge you guys for these sections is take a read through, at least a glance through these what do you call it, the textbook and the read through on it, because it's really going to cement a lot of ideas for you. It'll also give you maybe a different angle on an idea or concept that I've talked about. It'll give you some connections that you may not have gotten otherwise. The book is actually good to read through. So I challenge you guys to actually read through these sections, and this is where you can access that. Another note that again, I think I already said in the opening message to y'all, and y'all already kind of saw from the orientation module, but again, the homework that you guys are doing. So like I said, on every week in the module, you're going to see a little page for every homework. But that page is just a load button to get you into Cengage. And that's going to be your best way into Cengage, by the way. So actually, if you've noticed the way I've laid out this course, in the orientation module, you have the getting started with WebAssign page, which is again just a load button to get you into Cengage. From there, you basically your best way to get into Cengage is to click on the homework page and click that load button and get in there. But that's where you're doing the homework. So you'll see it in what do you call it? In Cengage. You'll see it in Canvas, the other sewer. You'll see it in Canvas, but it's just there so that you can press the button and get into Cengage, and that's actually where you do the homework. Now I've linked everything you're doing in Cengage to what you have in Canvas. So as soon as you do it in Cengage, you will see that grade, at least daily, they port those grades over to Canvas. So if you're looking for your grade in this class, you actually, again, your homework is in Cengage, but everything else we're doing in this class is in Canvas. So your gradebook for this class is the Canvas gradebook, and that'll have not only your homework grades that you're doing in Cengage as you do them, but it'll have then the test grades, the midterm and final that we go for us. Anyways, let me go find this other section. yeah, that's a good way to summarize this stuff. And then we'll do the analytic. And we'll talk about continuity. So we should talk about continuity probably in this section. Okay. And then give me a second. And then we also want to talk about, yeah, infinite limits. Ah. Yeah, but it's all that stuff. Well, let's at least start in 2.4. Hmm. See if I can get all these in the same view, maybe not. Is there any real difference between those? Hmm. Law. Okay, so I think what I'll have you guys do, so sort of sitting off to the side, you guys don't see me here on screen, but what I'm gonna have you guys do is I want you to do, so each of these problems, so if you look at sort of the way they laid out this exercise, each of these problems wants three things. They want the limit as x approaches the whatever value they tell you from the left, so that's part A, or I'm sorry, I guess from the right, from the left, and then they want the limit as x approaches that number. And I'm going to have you guys do that for, I think, 6. We don't need a ton of these, but let's do, I guess let's do 6, 8, and 9. So for 6, 8, and 9, I want you guys to find three things. So limit from the left, limit from the right, and then the overall limit for the x value. They're telling you they're telling you the x value by giving you the c value. Honestly, they also they essentially point the point out to you or point the value out to you. So anyways, so the way we're gonna do this is I'm gonna have you guys pause on your side, I'll pause on my side, and you just take the time to work out these three problems, 6, 8, and 9. And then I will unpause and and so once you're done with that, go ahead and unpause and we'll roll right on. I'll get work or just talk through the answers to those. So I'm gonna pause, you go ahead and pause and work on those three problems. All right, let's get back into this. Get this so you guys can actually see. All right, sweet. So 6, 8, and 9. Let's look at what these limits are. Let's look at what you got, what y'all got. So starting with 6. So we want the limit as x approaches. I'm not going to do the same order that they do. The left to right is makes more sense. So limit as x approaches 2 from the left of, we can say of f. And what did y'all get for that? Actually, sorry, it should be -2, not 2. Actually, give me a second, guys. Now I'm worried that I have the left and the right notations mixed up, which if I do, let's fix that for now. I do this occasionally. I flip things around. Blah, blah, blah. Let's see what the way they're doing it in this text. Blah, blah, blah. One-sided. Get to that. I want one-sided. No, I have it right. Okay. Okay, so back to this then. All right, so the limit that approaches -2 from the left on this, what did y'all say? So pretty obviously on this function, as you approach -2 for your x value, your y value is getting down to -2. Then the limit as x approaches -2 now from the right, this function, what did y'all say that was? Good, it's also -2, so on the right, my y value is getting down to -2. And therefore, what is my limit as x approaches, let's write this correctly, as x approaches -2 overall for this function? Good, it's -2. Again, left-hand limit exists, right-hand limit exists, and they agree, therefore the limit as x approaches -2 is -2. Good, box all that in. Now let's look at this for 7. So for 7, it looks like it was x approaches 3. So what is the limit as x approaches 3 from the left of this function? And what did y'all say there? Good. So coming from the left, you'll notice that as you get closer and closer to 3 for your x value, the y value is getting closer and closer to 0. As well from the right, so as x approaches 3 from the right side again, also your y value is going down and getting closer and closer to 0. Therefore, what's the overall limit? Good. The limit as x approaches 3 for this function is 0. But then for 9, so on 9, looks like our c or x value here is 2. So what is the limit as x approaches 2 from the left? And what did y'all say there? Good, that is 3. What is the limit as x approaches 2 from the right? From the left, my y value is 3, but from the right, it's approaching -3. Y value is -3. And so then what did y'all say for the limit overall as x approaches 2? Good. So the limit, I'm sorry, both of these were supposed to say f of x, f of x, f of x, all three of these. For f of x does not exist. It has to match left and right. All right, very good. Let me see. Let me see one thing here. All right, I think we're going to do something similar then for these. These are problems out of 2-5. But again, looking at this graphically, Maybe not as many of them though. I think we don't. Yeah, we just don't need to do as much. Um, I guess let's do this for 3 and 4. So what I'll have you guys do now is again, you'll pause video on your side. I'll pause it on my side, and I'm gonna have you guys. I'll change their instructions here. So this is again, this is number 3 and 4, and the exercises for 2, 5. Which again, you guys can open up that ebook and access all these exercises. So that's just a note too. As I'm doing this on the screen, hold on. Let me see. Let me see if the video got kind of wonky on this. It looks really grainy. No, no, no. It's still looking good on y'all's side. Um, but as I'm opening the yeah, actually self, I can just open up the ebook. So while you're doing this video, just have the ebook going. Um, the exercises we just did were in section 2.4. The exercises to begin with were in 2.2. These are in 2.5. I'm gonna kind of keep bouncing back and forth between them. You'll see as I go through this class that sometimes I use exercises in the book, honestly because they're there and they're convenient, especially for things that are visual. You'll see later on in the course when I do have to draw stuff out, I'm just slow with my hands, so especially drawing a picture out takes me some time. So especially with visual stuff, if they give me fodder to work with, oh, you betcha, I'm gonna use that. So you'll see as we go through this course that some portions of my lectures I'm using sort of some stuff or some problems out of the book. But other portions of the lectures, I'm actually going to be creating all the problems and exercises myself. Um, Rest assured, they're going to mimic the stuff you're going to see as far in terms of exercises. But there's some things, especially when we're doing derivatives and stuff like that, I don't need fodder. I don't need a book with a set of exercises. I can create all that stuff in my own head. I really don't need any of that. Um, so, um, so I'll just kind of do a bit of both as we go through the course. Either way, you'll see that like I said, the thing that I major on is I major on getting you guys to really grab at and understand the concepts and ideas. If you do some problems, but you don't get concepts and ideas, you are not going to get the material and you're going to suck at the test. um, what do you call that? Again, if that's probably not the way you've been doing mathematics, but just in case that's the way you've been doing mathematics, that's doesn't work. And that's why maybe you know how to do a problem, but you don't really know what you're doing or why you're doing what you're doing. And you guys are going on to become scientists, engineers, mathematicians. What you probably understand already, but if you don't understand already is, just to give you a little background, I started out my bachelor's of material science and engineering and was doing amazing, but I couldn't keep up with the workload. And so I switched to mathematics. So I was kind of seeing things both from a theoretical and applied side. So whatever major you are, as far as STEM goes, what you may have seen yet, but maybe you haven't, what you don't understand yet, is that when you're really solving engineering, science, math problems, um, it is not some replica of some problem you've seen before. But the concepts and ideas are exactly what you've seen before. So what I'm going to teach you guys as you go through this class is I'm going to teach you the concepts and ideas and get you to connect to that because concepts and ideas are your tools. It's literally your tool belt. That is how you do engineering and science. You do not do engineering and science by doing some problems that you've passed in a class. That you will not be able to handle the things in front of you. But if you know how to use the concepts and ideas that we're learning here, that you learn in a physics class or a chemistry class, etc., as tools, you can engineer, science, handle anything that you see. And then even go on to do research and things that we still haven't figured out, and you can eventually figure those things out. But you've got to use these concepts and ideas, and you got to use them as tools rather than just ways to get at a problem, basically. So you'll see as we go through this class, I'm really going to emphasize that. I'm going to emphasize even the way that I go through problems and get you guys asking questions and get you to think about how you're going to go through a problem. I'm going to teach you to use concepts and ideas as tools. Because that is the way, not only higher mathematics, but that is the way science and engineering works. You cannot do science and engineering if you don't approach that. So anyways, I forget what I was going with all that, but I'm gonna major on concepts and ideas. Yeah, so sometimes I'm gonna use the exercises in the book, sometimes I'm just gonna use my own stuff that comes out of my head because I've seen, like I said, I've seen the science and engineering side, and I've seen the mathematics side all the way down. I have a PhD in mathematics. I've published papers that are getting citations. I've seen the whole story. And so that's actually one of the reasons I love to teach higher mathematics is to me, I'm teaching story, teaching an idea, a concept, but I'm teaching story. Um, so, okay, anyways, so I'm gonna have you guys do 3 and 4 here. This is out of section 2.5. And I want you to do the same thing. So what we'll do here, so on both of these graphs, the thing that you're interested in is the x equals -2, and I want you to tell me what do you call it, the limit from the left, the limit from the right, and then the overall limit. So, so you pause on your side, go ahead and do that, I'll pause on my side as well. Let's get back into this thing. All right, so let's look at 3 and 4 here. What's the word I put it? So looking at number 3, and again, we're finding the limit as x approaches -2. So let's look at it from the left. So the limit as x approaches -2 from the left for f of x. What did y'all say for that? Good, and hopefully you said that that was positive infinity. Something again I wanted to emphasize, like I was saying when we were talking about these infinite limits before, for us we call these infinite limits. Again, if you were saying the limit doesn't exist, you're correct. So I just really want to emphasize when we say the limit is infinity, we're kind of talking about the behavior as x approaches 2 from the left. But infinity is not a number, it's not a resting place, it's not a certain thing, right? It's you keep going and you never end. So again, this is a very particular way of, so this is a limit that doesn't exist, but it doesn't exist in a very particular way and in a pattern that we can identify. We have a word for, we have a symbol for, etc. So the reason we write this infinity instead of does not exist is because that's, the limit does go to infinity. And again, like I was saying, you'll see then in chapter 3 when we talk about derivatives, and you'll see through the rest of calculus that even though, even though the limit doesn't exist, the fact that it goes to infinity, that's the pattern, that's the behavior, and that it's going to this one place, that pattern of behavior, that concept is actually crazy thing is it's useful. It's actually useful for things we're going to do with derivatives, and so it's a tool, it's an idea, it's a concept that we need, and it's useful, but it's not enough. So yeah, anyways, so I just sort of wanted to reemphasize those ideas. But the limit as x approaches -2 from the left is infinity. What about the limit as x approaches -2 from the right? What did y'all say there? And that is also going to be infinity. So if you look at this part of the graph, you're approaching from the right, you indeed are going up to infinity. Therefore, what's our limit as x approaches -2 overall? Good. That's going to be infinity as well. Again, not saying the limit exists, quote unquote, but it definitely has a consistent pattern of behavior that agrees from both sides. So that's our limits. Our limit is infinity. But then on 4, what did y'all say was the limit as x approaches -2 there? -2 from the left. From the left, as x approaches -2, my y value is going down to -infinity. So that should have been -infinity. What is my limit as x approaches -2 from the right? From the right, though, it's going up to positive infinity. And so what do I say overall? What is my limit as x approaches -2? Good. Hopefully you said it does not exist. So these do not agree, so I can't give a single answer. All right, good. Very good. All right, so one more idea that we need to talk about in what do you call it? Yeah, in terms of that grows out of limits, I'd say, in terms of limits, but really just kind of grows out of the idea of limits. So one more idea we need to talk about, and for that, doesn't matter where I start here, but let's start with some exercises from previous section. So I actually want to go back to 2.4. In 2.4, we did 6, 7, and 9 here. So I wanna go back and look at these particular graphs again. And let's talk about the idea of continuity or continuous. Let's do continuous. So we want to be able to identify whether these functions we're looking at are continuous. Again, I kind of want you to just think about the word. I'll give you a second. But what does that word mean to you? What do you think it means for functions? So the word continuous, just if you just think about it again, don't try to be fancy about it. You just think about everyday lowbrow. What does that mean? It kind of means something literally keeps continuing, right? So it keeps going. Maybe there's no sudden stops, there's no jumps or breaks in it. It's just like some path or process that just keeps going, a road that just keeps going. There's no real branch off, something like that. So maybe you said something like that, maybe it means something like that to you. In terms of functions, that's actually then what we're looking for. So I'll give you guys kind of the colloquial definition or visually what you're trying to go for. But then we'll talk about kind of how we identify a function being continuous, what it really means. So, but visually, that's actually what we're looking for. So something like 6, notice this graph. So my finger falls along the graph, the function, the path. There's no sudden jumps or breaks, there's no missing points, etc. It's just one smooth line, curve, whatever that's going to be, but it's smooth. Yeah, no jumps, breaks, missing points, etc. So that's basically, so colloquially, that's really what we mean by continuous. So what we mean, so let me make sort of an official definition out of it. So what we mean by continuous, well, in order for us to identify continuous, the first thing is that limit exists. Well, we talk about kind of two things. So functions can be continuous at a single value, and then we can say that a function is continuous over a whole interval or a whole stretch, or basically the whole function that you see is continuous. So I think what I'll do is I'm gonna write this definition more from the perspective of the function, the overall function being continuous over some stretch. So be continuous, first of all, the limit at every x value that you kind of see, the limit has to exist. So from the left and from the right, we have to have, it has to agree, it has the limit has to be the same value, the limit has to exist. Also, the y values have to exist everywhere. So again, going back to kind of the colloquial definition I gave to you guys, so I'm saying be continuous means that our function, first of all, our function, there's a point everywhere, so there's no gaps in your function. There's no sudden breaks or jumps. So sudden breaks or jumps are what we saw in our several examples we've looked at so far is often what makes things, the limits not exist. We can't have breaks and jumps. You can't have missing points. So the limit has to exist everywhere and the y values have to exist everywhere. You have to have a point everywhere. And then the limit has to equal the y value everywhere. So your limits has to exist so that maybe to again give you context of what we've talked about so far. So far what we've done in this lecture is we've just identified whether the limits exist. And we saw that one of the things that's curious, that's weird about that is it doesn't mean the point has to be there. So then to be continuous, like I said, continuous is sort of an outcropping and outgrowing of the limit idea. So for a limit, the point doesn't have to be there. Or the point could be somewhere else, right? We saw examples where the point is somewhere else. But to be continuous, the limit has to exist, but the point has to be there. And the point has to be where it should be. It has to match the limit. So the y value has to match the limit. And if you can say that a function that everywhere you're looking for that function, the little interval you're looking at, that in everywhere in that interval, the limit exists, but I mean, again, it's easy for the limit to exist. But also the point is there. Because again, for the limit, the point doesn't have to be there, but the point is there and the point matches. It basically, it fills in the hole. It matches the limit. It matches the y value that it should be. Then our function is continuous on that interval. So don't worry about some of this language. Let's talk about interval. That's one of those, it's a formal word that I'm trying to, as I'm doing this lecture, find maybe a more colloquial word to get you guys connected. But I'm not worried about you guys learning the rigorous technical definition of that. Good. So if you look at number 6 here, so for instance, number 6 that we looked at, we saw that the limit exists, at -2. But if you notice, not just at -2, but everywhere along this line, the limit exists. So everywhere along this line, the left and the right, from the left and the right, the y values match. So the limit exists everywhere along this little window. So window is probably the best word for interval. But along this window, everywhere the limit exists. The left and the right exist and match each other. And everywhere you also have a point that fills in. There's no gaps there. So just like there's a point here, there's a point everywhere here. Every bit of ink is a point. So the y value exists, or the point exists at every x value, and they match each other. So whatever point, whatever x value you're thinking of, let's say here, whatever that y value is, the point also matches that y value. So whatever that limit is, the point also matches. So that's what you're looking for continuous. So something like 6. So 6 is continuous. They're going to ask you, is it continuous? You're going to say yes, because everywhere along here the limit exists. Everywhere along here the point exists. There's a y value, and the limit and the y values match. Points just fill in right along the line. But if you look at 7, so notice, so the first question is, does the limit exist everywhere? And it does. So we saw the limit exists at 3, which is maybe visually our only problematic point. But everywhere else, you have nice little bits of it, you have nice little points. And from the left and the right, the limit values match. So the limit exists everywhere here. So on 7, if I'm asking if it's continuous, it checks the first condition, the limit exists everywhere. And it even checks the second condition. So everywhere along here, including at 3, there is technically a point. It ain't everywhere, even there. However, the limit and the y value don't match. And there's only one place that's a problem on 7, but you can see it pretty easily. We saw the limit as x approaches 3 is 0, but the y value, actually, the dividing on the point, or when x is 3 is 1. So this 1 doesn't match the 0. That point doesn't fill that gap. Therefore, 7 is not continuous on this window. Or you can say more specifically, 7, this function is not continuous at x equals 3. But either way, we're kind of, we're not technically saying the same thing, but we are kind of saying the same thing. We're trying to say the same thing. On this little window, this function is not continuous because we have a problem at 3. The y value doesn't match the limit. So 7 would not be continuous. And then if we ask that same question about 9, here, so the first thing you gotta check is does the limit exist everywhere? Here we even have a problem with that first question because we saw, again, we just saw earlier that the limit doesn't exist at x equals 2. So already that kiboshes the whole idea of being continuous because the limit doesn't even exist. Y values exist everywhere. There is a point everywhere here. But the limit doesn't exist, so I don't even have to worry about comparing the limits and the y value because the limit doesn't exist there. This one is not continuous. This one is not continuous because there isn't a limit everywhere in that window. 7 is not continuous because, not because there isn't a limit, but because the limit doesn't match the y value at x equals 3. Good. So we're going to keep talking about this idea of continuous because it's really important to derivatives and intervals, actually. So over Cal 1 and Cal 2, you're going to keep talking about this idea and using it because there are some conditions, basically. You can do derivatives in certain conditions, but not in others. And those conditions relate to continuity, so the function will be continuous. All right. So as a note then, second, let's go back to those examples we saw in 2.5. So, yeah, so we looked at 3 and 4 here. So 3 and 4 was asked sort of these same questions. This is 3 and 4 in section 2.5. And I'm not even saying in their exercises they don't ask this question, but it doesn't mean that a question can't be asked. We might as well ask the question. So on 3, let's look at 3, and I'm going to ask you, is this function continuous? What do you think? What would you say? And there's a couple different ways to answer this, but so again, to be continuous, we need the limit to exist everywhere in the window. We need the y values to exist everywhere in the window, and then in each case, we need the y value to match the limit. And so there might be a couple ways you think about this. This is not continuous. There's a couple basic violations here. Notice the first violation is actually that at -2 and 2, there is no y values. So we can't do it. It's not continuous. Also, you could also say that So we saw from our example, they were asking whether a limit existed at -2, and we said the limit was infinity. But remember, infinity is not a number. So technically, when you say the limit is infinity, you're still saying the limit doesn't exist because the number, it keeps going. The y values are going to keep going. They're never going to settle down to a certain value. So this has a second problem, which is the limit doesn't even exist everywhere on this window, on this interval. So this has two problems, but either one, you don't need, one problem is enough for things not to be continuous. You just need one thing to mess the whole machine up. So if they ask you whether it's continuous, you would say no, and then you would give one of those reasons. So that's what I forgot to mention with those last problems we looked at. So again, when you see these problems on the homework, what they're doing is they're going to ask you whether it's continuous, which if you think about it, it's just a yes or no question. But then they're going to ask you why. And you're going to have some choice, you're going to have a little drop down menu with some choices where you can say, one of those three reasons, one of those three things that make up the continuous definition. So that what I wrote on the board, that is again my colloquial but exact version of the definition for continuous. You just have to give one of those reasons. You'll see that here in homework. Okay, good. So yes, so definitely not just then 3. So then 4, again, it's not going to be continuous because we don't even have a y value at -2. And that kiboshes the whole thing to begin with. Now, for each of these, what you can say, if you kind of think about it, so if you look at not the whole window, but maybe, for instance, let's look at this little left portion, so up to -2, but not including -2. In that little area of the graph, it would be continuous. Because in that little area, the limits exist, the y values exist, and they all match each other. And then you could also say it's continuous from -2 to 2, not including -2 and 2, but in this little middle area. And you could say it's continuous from 2 to infinity, but not including 2. But you can't say it's continuous on the whole interval because it breaks one of the fundamental things we need to be continuous. So you can say something like that, which again, even if they don't do it in this homework, that idea is going to become really useful later. So don't just think about, later we're going to not just think about the whole window, but even on functions like this where it's not continuous on the whole window, we're going to break it up in parts and consider the parts. So at least we can do work on the parts if they are continuous. So again, you'll see as we go, being continuous is really important. Being continuous gives us something, it allows us to do work with these functions, work that we do in calculus. Okay. Let me show you one other small thing, and then that'll be it for this lecture. That is not it for the homework, though. So what I'm going to do in the next lecture, well, let me show you this other thing, and I'll talk about what the next lecture is going to be. So I want to go back to some problems in 2.2 just to mention. So some other, every problem that we've looked at so far, I'm talked about limits and I talked about continuity. All the functions were graphs, right? We know from, again, from college algebra pre-cal that I can show you a function as a graph, right? But that's not the only way I can show a function. I can show a function as a table. I can show a function as an equation. There's actually 4 different ways in general that we represent functions. But I can show you functions in different ways. What that means is I still should be able to identify or do the same work, identify the same things, limits and continuity of functions, whether I give it to you as a graph, table, or an equation. So I want to talk about a couple of the problems, or some of the problems you guys are going to see in the homework, especially in 2.2. What they're going to do is they're going to give you a table like this, so there may be something like 5. And they're going to go ahead and give you a table of x values, and then notice that the f of x values are missing. So what they're trying to cue you to do is they want you to fill in the f of x values for each of these. So they're going to give you the function. So literally what they're cueing you, what they're asking you to do is plug in 3.9 to this, and then type out your y value there. And they're probably going to ask you to round it to something, whatever they say to round it to, and then do it for 3.99, and then do it for 3.999. What I want you to notice is these x values are getting closer and closer to what? Good, they're getting closer and closer to 4. So in the middle of the table, you have 4. On the left, you have a couple x values that are close, closer, very close to 4. And then on the right, the same thing. You have some y values that are now to the right of 4, but they're close, closer, very close. So what they're trying to do is they're trying to get you in the table instead of a picture to do this limiting process, to figure out what x value are you getting closer and closer to. So that's really the goal overall of this table. So you're going to plug in these numbers and figure these things out, and then you're going to look at the pattern. So just like the x table has a pattern, we're getting closer and closer to 4 from left and right. So again, notice that's what you're doing here. It's literally they're giving you numbers on the left of 4 and the right of 4. So that's left and right limits. So you're going to see some y values on the left here, see some y values on the right here, and that's all going to get you closer and closer to some limit here. And you would think that you could just plug in the 4 maybe and get that number, but that's the surprising thing. That's what we're gonna kind of talk about as we go through the next lecture is these functions that I've been showing you these graphs for. The surprising thing is that usually at the number that they're looking for that limit, algebraically, there's something funky happening there where when you plug in the 4, you actually can't get that number. Can't get the y value. Sometimes you can, but sometimes you can't. And so what you're doing with this table is you literally are going to figure out what that number should be by the y values on the left and the y values on the right, and you'll see basically numerically what y value they're getting closer and closer to. Just like the 3.9, the 3.9, the 3.99 are getting closer to 4, etc. So you're going to have a couple problems like this, and they're going to give you some regular, this is a rational function, you saw that before. They're going to start giving you some odd mix of functions like I was talking about. But either way, all you got to do is plug in the values. In general, what I'll say is, though, if you plug in the middle value, what you're actually trying to find the limit for, it's not going to work in that function. You're going to get, it does not exist. It's going to be something you can't calculate. So you're going to use the y values you get out of these, the left and the right side, to guess that value there. And it'll be pretty apparent. So you're gonna have some problems like that. Now, notice though, if you're doing something like this, like I just said, and hopefully that didn't skip past you, you end up having to guess at this value. And if you think about the other problems we did today, so I gave you graphs of functions, and we would figure out the limits, but honestly, they both drew the graphs in very, in a certain way, and picked special values where you kind of could see the y value on the graph and you knew what they were intending, right? You knew what they were going for. One of the problems with representing functions as either tables or as graphs is that's the issue, is that especially with the graph, we assume we know what the y value is by the picture, but we actually can't tell usually exactly unless they put special marks there or just design the picture well enough that you sort of know what it should be, right? And with a table, you end up with the same issue. So again, if I can't plug in this middle value on any of these tables, I'm going to get these 3 values on the left, 3 values on the right, and I'm going to take a good educated guess at that middle. But actually, that's not an exact value, that's not an exact figuring out, that's an estimation. That's not really mathematics. It's calculation, it's arithmetic, but it's not mathematics. Because in mathematics, we try to figure out what is the exact value? What does it have to be? Not what should it be? What does it look like? What do I think it's getting to, right? So I will say with the first half of the work that we're doing with limits, so in all these sections, 2.2, 2.3, 2.4, and 2.5, you're technically doing guesses. They're good educated guesses or good, well-designed guesses, but they are just guesses. So the question then becomes, like I can tell from the table and the picture that there is definitely a limit, right? We established that there's a limit, we sort of have a definition for that. So, but if the picture and the table ultimately only gets me a well-designed guess, how do I actually figure out the limit definitely, algebraically, mathematically, without any guesses? And the way we do that is from the function itself, basically. So what we're gonna look at in this next lecture is, instead of looking at a graph of the function or a table of the function, we're gonna look at the function itself, the actual equation for it. And we're gonna use that to find these limits exactly in every scenario. Actually, basically, we're gonna look at sort of every scenario we just looked at, or a lot of the functions that you guys already know from all of algebra and pre-calc. And we're gonna go and look at how do we find that limit exactly. What do you call that? Yeah, so that'll be the next lecture. But once we have that, that'll actually get you everything for this week. So week 1 of Calculus 1, Summer 2, 2025, you will only need 2 lectures. You'll need this, and you'll need the next lecture about how we find these values exactly using algebra. And once you have that, though, that'll get you everything for these 4 homeworks, 2.2, 2.3, 2.4, and 2.5. So that'll be it for this lecture. Come back for one more lecture. You'll see it on your little lecture pages, lectures page for week 1. And then you guys will be good. You can run through all the homeworks. So I'll see you guys for the next lecture.